Polymer chemistry explores how chemical composition and molecular structure govern bark properties and performance of complex, heterogeneous polymeric materials influenced by surface composition, morphology, crystallinity, and additives. No single technique suffices for full analysis. Comprehensive characterization combines chemical methods like FTIR spectroscopy for functional groups and identity, with morphological tools like SEM-EDX for surface features and elemental distribution. This multi-method approach enables targeted design of materials with desired strength, stability, and biodegradability. The objectives of this analysis is to characterize the chemical structure and composition of plastic bag using Fourier transform infrared (FTIR) spectroscopy, and to examine the surface morphology and elemental distribution of the plastic bag using SEM.
This slide shows the ATR, FTIR analysis procedure for the plastic bag sample. First, the plastic bag was cut into small pieces measuring 2 by 2 cm and cleaned to remove any surface dust. Second, the ATR crystal and pressure tip were cleaned with ethanol using a Kim-Tap wipe to avoid contamination. Next, a background spectrum was recorded before the sample analysis. After that, the plastic sample was placed on the ATR crystal and the pressure was applied to ensure the good contact. The spectrum was recorded in a range of 500 to 4000 inverse centimeters using a resolution of 4 inverse centimeters with 16 scan. Finally, the ATR crystal was cleaned again after analysis to ensure no residue remains, and the infrared spectrum will automatically process using OPNIT software.
For SEM analysis, the plastic bag was first cut into small 5x5 mm pieces and handled using tweezer to avoid contamination. The sample was mounted on an aluminum stub using carbon tap and gently pressed to ensure good contact. It was then spatula coated with a thin layer of platinum to prevent charging. Finally, the sample was placed in the SEM chamber and observed at a low accelerated voltage with magnification adjusted to obtain clear images.
For this part, I will be discussing the FTIR results of the plastic bag sample. FTIR was used to identify the chemical structure of the material by analyzing its functional groups and confirming the polymer type. This slide shows the FTIR spectrum of the plastic bag sample. The strong peak at 2913 and 2845 per centimeters correspond to CH3 vibration or CH2 groups, also known as methylene group. This indicates that the polymer backbone mainly consists of no hydrocarbon chains, which is typical for polyethylene plastics. The peak at 1462 per centimeters is related to the bending vibration of CH2 groups, further confirming the presence of repeating methylene units. In the fingerprint region, a strong peak is observed at 718 per centimeters. This peak represents the rocking vibration of repeating CH2 units and is considered a fingerprint peak for polyethylene. A weaker peak is also present at 873 per centimeters. Even though this value is higher, the peak is less intense because it involves fewer molecular groups, possibly due to minor branching or structural irregularities. There are no significant adsorption bands were detected in the carbonyl or hydroxyl regions. This suggests that the plastic bag sample has not undergone significant oxidation or chemical degradation. Overall, based on the FTIR analysis, the plastic bag sample is identified as polyethylene. The dominant CH2 stretching, bending, and rocking vibrations indicate that the material is most likely low-density polyethylene, which is commonly used for flexible plastic bag.
So now we go to the discussion of the SEM analysis. So this slide shows the SEM image of the plastic bag at a magnification of 100, which provides an overall view of the surface morphology. This surface appears smooth and continuous with no visible cracks, tears, or major defects. This suggests that the plastic bag maintains good structural integrity despite regular use in market environments. Some small bright particulates can be observed on the surface, which may be due to surface contaminations or additive in the plastic. Overall, at these magnifications, there is no evidence of severe degradation. At a higher magnification of 500, finished surface features become more visible. Linear saturations and shallow grooves can be observed across the surface, which are likely associated with the film extrusions and stretching processes during the manufacturing. Small particulate features are also present, possibly originating from the additive handling or sample preparations. Importantly, no significant microcracks, deep fissures, or surface erosions are detected. This indicates that the plastic bag has not undergone extensive microscale degradation and that the polymer matrix remains largely intact. Overall, SEM analysis at both modification shows that the plastic bag surface remains structurally stable with only minor surface irregularities and no.
In conclusion, this analysis successfully characterized the chemical composition and surface morphology of the plastic bag sample using FTIR spectroscopy and SEM analysis, achieving both stated objectives. The FTIR result confirmed the material as predominantly low-density polyethylene, and the SEM micrographs at 100 and 500 magnifications revealed a largely homogeneous surface. The combined techniques demonstrate the value of multi-method characterization in linking polymer chemistry to performance, offering insights for assessing environmental, persistent, and recyclability of everyday polyolefins.